Wow, that was a very impressive response time, Delhi. Thank you. So it's my great pleasure to introduce our speaker, Ruonan Han, today. So Ruonan is an associate professor. He's joining us from MIT, where he's an associate professor at the Department of Electrical Engineering and Computer Sciences. And he's also a core faculty member at the Microsystems Technology Lab. So Ruonan received his bachelor's degree in microelectronics from Fudan University in 2007, did his master's in electrical engineering at the University of Florida in 2009, and obtained his PhD degree in electrical and computer engineering from Cornell. And he's been at MIT, leading the terahertz integrated electronics group since 2014. His research focuses on RF to photonics integrated circuits and systems for spectroscopy, metrology, imaging, sensing, and communication, broadband secure communication applications. So he's kind of both on the circuit side, but he's also very interested on the applications in many different domains as well. And today he's going to be telling you about some of these applications. Before starting the talk, I want to highlight some of his awards. There are several of those. He was the recipient of the Cornell EC Director's PhD Thesis Research Award. He also received the Cornell EC Innovation Award and 2 Best Student Paper Awards of IEEE Radio Frequency Integrated Circuit Symposium in 2012 and 17. He's also got several awards, graduate fellowship awards from IEEE Microwave Theory and Technique Society, Solid State Circuit Society, and he's an associate editor of IEEE Transactions on Very Large Scale Integration Systems and IEEE Transactions on Quantum Engineering, a guest associate editor of IEEE Transactions on Microwave Theory and Techniques, and also serves on the technical program committee of the IEEE RFIC Symposium. He is the IEEE MTTS Distinguished Microwave Lecturer from 2020 to 2022. And in addition to all of these, he recently won the Intel Outstanding Research Award in 2019, and he was also awarded an NSF Career Award in 2017. So without further delay, I want to kind of leave the stage to Ruonan, who's going to tell us about chip scale wave matter interactions at RF to light frequencies, from circuits, systems to applications. Take it away, Ruonan.
Thank you. Good afternoon and maybe good evening, everybody, for joining this talk. So it's my great honor to be invited to present my research to you guys. So as Alp just introduced, my major research is on terahertz integrated circuit design. So I'm a circuit designer. This talk is a little bit different from that. So basically in here, we're interested in chip scale wave matter interactions, especially, I mean, I'm not a physicist, but I'm really interested in linking the low cost and large scale integrated systems with some physics and their applications. All right, so let's get started. So first of all, this talk is really about electromagnetic spectral sensing on the chip. So if you really think about the nowadays on-chip EM sensing, the common applications we can think about is, radars on the car, gesture detectors, millimeter wave, all the way to visible light imagers. So I would argue that these sensors really share some commonalities. For example, we are really using frequency insensitive EM scattering of macroscopic objects that are located in a remote distance, okay? And while this category will continue to thrive, I would argue that there's actually an emerging area that is coming up. So in this new area, we basically still use chips, but we use a high precision and frequency selective waves to directly interact with some quantum behaviors of microscopic particles, such as molecules or electrons that are located in close proximity with the chips. And there could be some very interesting applications. For example, shown here is what we call chip scale molecular clock, where you can translate the rotation of molecules into some very stable clock frequency at the output. All right. First of all, some basics about wave matter interactions in different modalities. In the megahertz range, as we know, we have a nuclear magnetic resonance, And then in the gigahertz range, we have electro spin resonance. And now if we can push the frequency to low terahertz regime, we start to excite the rotation of molecules. And then in high frequency terahertz or IR, we start to have vibration of molecules. And there's actually quite some applications associated with these. And of course, the most fancy buzzword these days is quantum computing. In addition to that, I would argue there are also some other applications, and I divide them into three categories. The first one is material identifications. So different molecules, for example, under the illumination of terahertz would have very unique rotation frequencies. So in a transmissive setup, if you're able to detect these transition lines, then you can precisely identify what kind of materials you have in the sample. And also some quantum behaviors tend to have very big sort of susceptibility to environmental disturbance. For example, if you look at the rotation of or spin of electrons, it basically has pretty strong magnetic dipole. And now if you apply a magnetic field around it, you start to lead the Zeeman splitting, as we know. And that way, if you can detect the splitting energy, then you can translate that into the magnetic field you have. And in comparison, some other quantum systems tend to be very robust. For example, if you take a look at the rotation of some polar molecules, in this case, it's a rotation of carbonyl sulfide. My favorite molecule, or OCS, essentially have a positive charge, negative charge, and they co-rotate together. And if you think about the net current generated by this system, it's very small. And as a result, you have very small magnetic dipole, okay? Beside the molecule is also much heavier compared to the electrons. And because of this, the transition frequency of this rotational energy is very stable, okay? And instead of doing a sensor, you can actually turn that into some metrology system. And in this case, it's a frequency reference, all right? So these are the sort of applications that we are interested in. And not only us, a lot of people, they are working on this. But if you take a look at a lot of current hardware systems, they're either very big or still very expensive. And some of these setups, for example, this one, I wouldn't even call that a hardware. It's essentially a lab setup, okay? So I think it's going to be really impactful if we're able to really shrink these devices down to the chip scale with very low cost technology. That way, we can enable quite some applications, which are accessible for everybody. And people are working on that. Here, I just give you some examples coming out of the Society of Solid State Circuit. Some people are working on, nuclear magnetic resonance sensors, and, of course, quantum control these days are very popular. In this talk, we are going to introduce a few examples from my group, utilizing the sensing in the electronic spin resonance, and also metrology and sensing based on molecular rotation, for example. So this is the outline. So I will basically focus on three prototypes. The first one utilized the rotational spectrometer in terahertz to do gas sensing. And the second one is based on the same principle, but now we change the application to metrology to generate a very stable clock signal. And the third one is a room temperature quantum magnetometer. And after that, I will conclude my talk. So the first one, rotational spectrometer. So here's some basics. If you just imagine you have a polar molecule which carry either electrodipole or magnetic dipole, and now if you shine a wave onto this molecule, then you start to exert the torque onto the molecule and make it rotate. And it turns out that the rotational energy is also quantized. And for a linear molecule, the quantization of the rotation energy follow this equation. So this J in here is the quantum number. And if you really take a look at the resonance frequency, allowing the molecule to jump from one energy level to the next one, which is expressed in here, you can see that they're actually equally spaced in the spectrum. So this is called the rotational spectrometer. And it actually turns out that for most of the molecules, the transition frequency is as low as in the RF or microwave regime. So then the question is, why do we do this spectrometer in the terahertz, which is obviously much hotter? So here are some arguments, and this is actually the argument that I like the best, because it sort of tell you why terahertz is unique in here. So in terms of the energy of rotation, it turns out that in addition to this quantum number J, for each energy level, we also have degenerated quantum states. And if you look at the physics, as you have higher frequency or higher quantum number, you tend to have more and more quantum substates or degenerated states. And all these states actually contribute to the transition from one level to the other, which means that now if you have higher energy levels or higher frequency, you start to have higher and higher absorption intensity. So that gives you higher SNR and also higher sensitivity in your sensor. But beyond a certain level, in this case, beyond about half terahertz, the absorption actually decreases. And that is because the Boltzmann distribution kicks in, which tells us that now for higher energy levels, the probability that the molecule is at that state to begin with is much lower. It actually decreases exponentially. And then even though you have more degenerated substates in there, the overall absorption that the molecule can have, jumping from, for example, this energy state to the next one, is still much lower. All right. So if you combine these two factors together, the conclusion is that for rotational mode absorption, the peak intensity normally happens in the terahertz regime. Okay, so that's why we prefer to use terahertz for these spectrometers. And in addition to that, we also did quite some experiment just to check what the transition line looked like. And it turns out that under some low pressure, we actually can have very narrow transition lines. For example, for a center frequency of 267 gigahertz, you can see that the line width of the transition could be as small as a few hundred kilohertz. So we are really talking about a quality factor that is close to 1 million, which is phenomenal in the gas sensing. So normally you can easily confuse from one molecule type to the other if they have overlapping in their transition lines. But here, the chance that the transition lines have overlap is much smaller. Okay, so some chemistry papers actually call this absolute specificity, which is a really powerful feature. And of course, as I mentioned, some of these transition lines tend to have very high stability, which is good for metrology systems. So now in terms of the applications, here I just list you a very small portion of a large list of detectable molecules in the window between 200 gigahertz to 300 gigahertz. So you can see that they have very unique transition frequencies, and also they are either toxic or flammable. So obviously it carries a lot of significance if we can detect and also simultaneously detect these molecules out of a single device. And this is not only meaningful for example, air quality monitoring, but also for some health condition monitoring. It also is very important. So far, people mostly focusing on using some bulky, commercial terahertz transmitters and receivers to build terahertz rotational spectrometers. One classic example in here is shown, which is from the University of Ohio. And what you can see is, the overall system is still pretty big. But of course, it carries nice features like absolute specificity and also very good sensitivity. So it is really our interest to see whether we are able to shrink all these devices down to chip scale, especially onto a CMOS chip, which has a very low cost. But silicon transistors are never well known for their speed, right? So they're actually slow. And what you can see in here is in particular, the Fmax, or the speed of the transistors, is really not scaling well with the size of the device. Definitely not the same as the digital counterpart. So we have to rely on, for example, some harmonic generations to really reach the terahertz regime. It's not that efficient, but with quite some circuit tricks over the years, people have demonstrated that you can still get nice results. For example, nowadays, the coherent radiated power from these silicon devices can reach multiple milliwatt in the low terahertz regime, and even at 1 terahertz, now we can generate about 100 microwatt of power. So this becomes a possibility. Do we have any other challenges? So here's actually one that is closely associated with terahertz rotational spectroscopy. So basically, there's a fundamental trade-off between efficiency, the band coverage you need, and also the resolution. So here I just give you some data. As I mentioned, the transition lines are normally equally spaced in the spectrum for linear molecules, and the spacing between two adjacent transition lines of a molecule is actually a function of its molecular structure, especially its weight. Okay, so normally heavier weight will give you more dense spectral lines. So that means to detect some light molecules, for example, in this case, hydrogen cyanide, you really have to get a really big window, because the chance that you can capture one line is much smaller. So in this case, the spacing between two adjacent lines for hydrogen cyanide is about 89 gigahertz. So you really need to have a wide enough window to simultaneously capture a lot of possible molecules. So our target is about 100 gigahertz window width, and that way we can have a wide detection range. But don't forget, the transition lines are very narrow, okay, a few hundred kilohertz wide. So that means we need to scan this really broad bandwidth with very small resolution, okay, or very high resolution, normally at the tens of kilohertz range, and that could lead to very long scanning time. And also, this large bandwidth normally require you have a tunable but normally very lossy device in the terahertz regime. And if you also want to use high Q resonance to recycle some power here and there from your circuit, that also hurts your bandwidth. Okay, so there are quite some trade-offs here and there. And I think this graph sort of tells you that trade-off. So in the past, if you really look at the output power versus the fractional bandwidth, there's this very clear trade-off between the two metrics. So long story short, a few years ago, we proposed this what's called bidirectional dual terahertz frequency comb spectrometer in CMOS. And essentially what it does in here is that instead of using a single tunable output tone to really scan this wide bandwidth, in here we basically use a lot of frequency tones in parallel, okay? So in this setup in here, we have two identical CMOS chips, and one chip essentially generate 10 equally spaced lines, so that's why it's called comb, and also detect the other 10 frequency lines that are generated from another CMOS chip, and down convert those 10 lines down to baseband or IF frequencies, and what you can see in here, okay? So altogether then we have 20 frequency comb lines that are simultaneously scanning this 100 gigahertz bandwidth. Then naturally we can increase the speed by a lot, at least 20x. And also more importantly, now we have dedicated transceiver that is only in charge of 10 gigahertz bandwidth to do signal generation and then heterodyne down conversion at the same time. That way, these transceiver circuits can utilize quite some circuit tricks. For example, high Q resonance, and also we can intentionally introduce some controlled positive feedback in the device to really increase its active gain. All right. None of these are possible if you want to really use a single circuit to basically scan a wide frequency range. So here's the architecture. So basically we use a centralized L generator chain to generate different frequencies with multiple frequency mixers. Then we have a dedicated transceiver to take that L signal, multiply it, and radiate out. And also at the same time, we can receive another tone through the same antenna, and then perform heterodyne down conversion inside the transceiver and down convert it to the IF signals. And now if I just sweep this centralized LO signal chain in here, all these 10 frequency lines will be scanned at the same time. So this sounds to be a straightforward architecture, but the biggest challenge actually lies in this terahertz front end. Because you have to make it very compact in terms of the size, and also you have to design it to be very energy efficient. Otherwise, your chip will be too big and also too power consuming. So the actual circuit design is out of the scope of this talk, but in here I just want to sort of give you some taste regarding how the circuit is generally designed to mitigate those problems. So basically, our strategy is called a multifunctional electromagnetic structure, and the idea is, instead of using discrete, like a separate circuit components to achieve different tasks, here we basically want to use a single EM structure that can perform differently for different frequencies, for different signals, and then you have much higher efficiency and also much smaller circuit. For example, in here, this is the last stage of our transceiver, where we have two transistors to really double the input L fundamental signal to generate terahertz signals, and then we want to radiate it out, and also we want to receive another signal and do the heterodyne down conversion. And in this circuit, we have just two slot lines, and slot 1, which is a folded slot in here, and the slot 2, which is this one in here. And the operation is like this. So for the fundamental input signal, we do that differentially to send the signal through this microstrip line into the gates of the transistors. So in here, what you want to do is to really increase the nonlinearity of the transistors to generate second order harmonic signals. And to do that, you want your voltage swing at the drain to be as large as possible. So that's why this slot is designed to be quarter wavelength. That way it behaves as a resonator and really boosts up the voltage swing in here. What's important also is that this slot line, which is called the defected slot line in the ground plane, is that it can carry some of these amplified power at fundamental frequency back to the input to create some positive feedback. That way we don't really waste the fundamental power in here, and we can increase the activity of this transistor. And this is naturally happening because these two sides on here are differential, so we actually excite quasi-TEM mode inside of this slot line, and then the signal is carried back to the input. But now, for the second harmonic signal, which is what we want, what you can see is out of the nonlinearity of the transistors, we not only just double the frequency, but also we double the phase. So now the signal on the two sides are in phase. And what's happening is this slot 1, which was the resonator at fundamental frequency, now naturally turns itself into slot dipole antenna, okay? Because the field inside are actually in phase. So instead of having a dedicated separate antenna, now you can directly do the radiation. And also for this frequency, we don't want to recycle power back to the input. And that's also naturally happening because now the two sides of this slot is in phase. And in order to carry a wave inside the slot, you have to get a TM mode wave inside the slot, but that's not possible because there's a cutoff frequency associated with this TM wave. So this this slot 2, which was the recycling path for the fundamental frequency, now is naturally blocking this desired second order harmonic signal from doing that. And then you can directly just do the radiation. So basically in here, we use very simple structure to perform multiple functions at the same time. That way you have both efficiency and also compact size. So with that, eventually this is the chip that we implemented. The size is about 6 millimeters square. And here we have 10 transceivers with their built-in antennas. And also these 10 transceivers are tuned at different frequencies. So obviously this has a pretty large integration level at the terahertz frequencies. And the DC power is about 1.7 watt. So here are some measured electrical performance. I think what's significant is now, because we use this high parallelism architecture, we really don't have a performance degradation on the two edges of the band, which is normally the case for a single cone architecture. And also here you can see that we radiate 10 equally spaced frequency lines, which is the cone spectrum. And here's the fun part. So to demonstrate the gas sensing, here we have a gas chamber where we can insert any molecule gas or combination of different gas samples. And here I have these two CMOS chips to do basically the transmissive spectroscopy. The measured absorption-free signal-to-noise ratio is about 98 dB for 1 Hertz bandwidth. So that sort of shows you how much link budget we have, which eventually turns into sensitivity. And here's just one demo. We insert the combination of carbonyl sulfide and also acetonitrile molecules with a certain ratio. And what you can see is across this 100 gigahertz bandwidth, the chipset is able to generate all these fingerprints from the molecules. And actually, if you just zoom in into a small section of this spectrum, you can see all these tiny spikes which are associated with the transition lines of molecules. And this, again, shows you this absolute specificity feature of the sensor. We also measure the signal-to-noise ratio at a different concentration level and conclude that for molecules like carbonyl sulfide, the sensitivity is about 10 ppm. And again, this is actually without any pre-concentration of gas, which is the standard in gas sensing or spectrometer. With a standard pre-concentrator, we anticipate that the sensitivity can reach ppb or even sub-ppb level. All right. So this sort of shows you how a CMOS chip is able to smell. Okay, smell without having chemical reactions inside. So this could, in the future, be a low-cost gas sensor. And next, let's change the direction slightly to metrology applications. So during our experiment for this spectrometer, we start to realize that these transition lines that we measure can actually be very stable and precise. And you can actually see how many digits we have in here. So that sort of indicates that if we can turn this into a stable output frequency, then we have a very nice clock. And this is essentially why atomic clock is much more stable than crystal oscillator, which is highly dependent on temperature and also the size of the crystal itself, right? Here are some background information about the comparison of frequency references. So there's a very strong dependency between stability and power consumption and size, as you can imagine. For normal devices, people use crystal oscillators. But if you want to have, for example, some advanced functions for example, inertial navigations or base stations in the towers, in the cell phone networking, then you need to have much more stable clocks. Okay, so then people start to consider, for example, atomic clocks like a rubidium clock, cesium clock, but these clocks normally burn a lot of power and they tend to be very expensive as well. But some new applications these days really require references that can break this trade-off. For example, if you take a look at the 5G networking, phase and also time synchronizations among base stations is actually very important people tend to have, for example, carrier aggregations or even positioning using these infrastructures. And for that, sometimes you need to have below 100 nanosecond timing error among these infrastructures. So of course you can use GPS signals, but just in case that the GPS signal is disrupted or unavailable for a while, you need to have very stable local clock holdover clock to do the work. Okay, and if you just do the math, if you want to hold that time for 1 hour, then the stability needs to be on the order of 10 to the minus 11. And that's pretty hard because nowadays we need to have massive deployment of these base stations. And for 5G, the size of the base station is also much smaller, and also people tend to be more sensitive to their power consumption. So you not only just need stability, but also low power and also small size and also low cost. So talking about that, I think one huge success in the past is called the chip scale atomic clock. And essentially, I call that a masterpiece of engineering because essentially people just, shrink a lot of necessary components for atomic clocks down to a really small scale, as you can see in here, and they can still perform all these atomic interrogation. And out of just 100 milliwatt of power, people can get 10 to the minus 11 stability across a 100-second time scale. But there's a still problem associated with this clock. Essentially, it's really complicated. You need to have high cost and high precision electro-optical components that are really miniaturized. And as a result, even now, if you go to the market, the price of this kind of clocks is still a few $1,000s. So we were like, okay, now since we have our own CMOS spectrometer, which can smell different gas, how about we just seal some known molecules, in this case it's OCS or carbonyl sulfide molecules, inside a single mode terahertz waveguide. And then we use a CMOS chip to really launch the wave into the waveguide to really detect the rotation of molecules. And then we build a feedback network to regulate the output frequency of a crystal oscillator. That way we can have the similar principle or similar operation as an atomic clock, but now everything is fully electronic, and also the construction is much more simplified. And as a result, we hope the cost can be much lower, and also the size and the power can also be low as well. So that is the idea. And it turns out that we are not the very first one thinking about molecular clock. Molecular clock turns out to be even invented before the invention of atomic clocks. So even 60 years ago, people in NIST, they actually want to detect the vibration of ammonia at about 23 gigahertz and then turn that into clock output. And they succeeded. But what you can see in here is that, of course, the generation of 23 gigahertz even 60 years ago would be a challenge. And also, if you take a look at the comparison in here, the vibrational mode of ammonia at 23 gigahertz is actually much weaker in terms of the power absorption compared to OCS transition at sub-terahertz. So as a result, you need a very long waveguide, and also lower frequency means the waveguide is much fatter. Okay, so because of all these, eventually the researchers turned their research directions to atomic clocks, and this idea tends to be forgotten. But now we believe we can revive this idea of molecular clock. So here's one prototype that we did just to demonstrate the idea. Essentially, we use a commercial terahertz transmitter and receiver, and also a customized CNC machined gas cell as the terahertz waveguide to seal the molecules inside. And indeed, we saw that the Allen deviation can be pretty good. Okay, at 1,000 second, we can get about 2 times 10 to the minus 11. And that's already pretty close to what the chip scale atomic clock can get, which was pretty encouraging. And this is probably more straightforward, in comparison with the crystal oscillator in the free running mode inside this setup. You can see that with the regulation, now the output frequency is much more stable over a longer period of time. So that's exciting. And then a few years ago, we took one more step and really aggressively, shrink all those necessary hardwares onto a 65 nanometer CMOS chip, which is shown here. So basically, what we have on the transmitter side of this clock is a sub-terahertz phase-locked loop with low noise and also very high resolution, basically 10 to the minus 12 frequency tuning resolution. And we use this to essentially detect the rotation of molecules. And also we have on-chip locking, the terahertz square law detectors and locking amplifiers to recover the absorption, and then we build the feedback. So here are some more details. Essentially what we're doing here is that out of a probing frequency, we perform a FSK on top of that so that the signal is actually jumping back and forth on the two shoulders of this spectral line, as what you can see in here. So if my instantaneous probing frequency precisely align with the valley of this transition line, then when I do this FSK, I really don't have, I really don't observe the fluctuation of absorption on the receiver side. Then with the locking amplifier, I generate a zero error signal, indicating that no change is needed. But if the frequency is lower than the valley transition line in here, then when I do this FSK modulation, the absorption will be fluctuating. And also then after the locking detector, a negative error signal will be generated, indicating that I need to pull the frequency up. Same thing if the frequency is higher than needed, then the locking detector will detect a positive error signal, because here the fluctuation of the absorption has the opposite phase compared to this, okay? And then we can also adjust the frequency accordingly. So if you really take a look at this entire operation, this chip is basically doing this. The chip is changing the frequency in the X scale a little bit, and in the real time monitor the change in the Y scale. And that is equivalent to having a first order derivative of this transition profile, okay? So now if I consider the Y scale to be my center probing frequency and the Y scale to be my error signal, and if I do this sweeping, then essentially what I generate out of the chip is the first order derivative of this entire curve, and people tend to call this dispersion curve of the transition line. And eventually in the steady state, the clock is locked at this zero crossing point of this dispersion curve. So here's the package.
Ronan, I have a quick question.
Yep.
Were you using this technique for your earlier plots as well? You had some curves that looked like derivatives earlier in the talk.
You mean from the lab scale clock, right?
Um,
Which one are you talking about?
Just when you were showing, absolute spectroscopy of molecules, the line shapes there, were they also derivatives?
Well, actually, a good question. So for my gas sensing, when I show these spikes in there,
Yeah.
those we actually detect the basically the second order derivative of this curve.
Okay.
And very soon I will talk about that too. So you can just imagine that the chip is actually generating the second order derivative of this curve, and then it will basically have the peak right in the center in here. So that's why we show that at that transition frequency we have those peaks.
Okay, thank you.
Okay. All right, so this is the package of the clock. Here we basically use an external quartz probe to send the terahertz wave into the terahertz waveguide. And the size is about a matchbox size. It's bigger than what we wanted, but because we may still need to make connections to all those vacuum systems. But the actual encapsulated OCS gas volume is about 80 millimeter cubes. So you can consider this to be the ultimate size. And the terahertz system is normally considered to be power inefficient. But here we show that since you only need to probe molecules that are very close to your chip, and these molecules actually will be saturated if you launch too much power into it, then we don't need to have much terahertz power, and the overall power consumption of this whole thing is below 70 milliwatt, which is actually even better than the chip scale atomic clock now. And you can see that the chipset is able to generate this dispersion curve. And when we log onto this zero crossing point, we get this Allen deviation. So this prototype gives us 4 times 10 to the minus 10 Allen deviation, which is about 10 times worse than our lab scale clock. And there are multiple reasons for that. For example, we realized that this waveguide coupler actually has about 10 dB of loss. So we lose a lot of signal to noise ratio. But also you can see that this Allen deviation plateaus at about like a tenth of a second, rather than, keep getting this averaging out and get better and better. So the reason was because of the temperature fluctuation. Ideally, the transition line shouldn't be affected by temperature, but it turns out that our baseline of the spectrometer is tilted a little bit. This is due to uneven frequency response of my electronics, and also some wave reflections inside of the waveguide. So we have a slight tilting of the baseline. So now the overall measured real spectral curve is the superposition of this ideal symmetric curve and also this tilted baseline. So now the overall curve is asymmetric. And now if I take the first order derivative of this curve, I have an offset, okay? And this is the problem, because I still log to this zero crossing point. And now if you change the temperature, which means that the absorption intensity changes, now I have some different zero crossing frequency due to this offset. And that's why I have this plateau of Allen deviation curve. So how do we solve that? One pretty straightforward solution is, instead of taking the first order derivative, here we can actually take the high order derivatives, for example, third order derivative. That way, if you do the higher order dispersion, then that fixed offset goes away. And now your zero crossing point is still what you want now, and it's relatively temperature insensitive, okay? So now we can have a much better stability, but that requires you to, instead of doing FSK modulation, to just jump back and forth on 2 discrete points on your transition line. Now you need to do a continuous FM sweeping of the entire curvature of this transition line to extract all these curvature information, and that makes the circuit design much harder. So to do that, we actually developed the second generation molecular clock last year. This is obviously pretty complicated, but the basic idea now is I can extract the third order harmonic or derivative of this transition line curve, and then I can have much more stability. And also now we have a single chip integration rather than a discrete transmitter and receiver chips. And as I also mentioned previously, we had this problem of coupling the wave to the terahertz waveguide. Now we took a different approach. We actually use an integrated waveguide coupler to do the work. It is essentially a 2x2 slot antenna to directly radiate the wave from the chip through the silicon substrate directly to the waveguide opening on the back of the chip. So that way we don't need to use any external components for the wave coupling. It becomes much simple in the packaging, and also the insertion loss becomes smaller. So here's the package. It's slightly smaller than what we had before, and also we managed to keep the power consumption to be the same. And now what you can see is the chip is able to generate a third order dispersion curve of the transition line. And in terms of the Allen deviation, now we can reach about 4 times 10 to the minus 11 at 1,000 seconds. Actually now we have a third generation, which is not published yet. And we are able to reach about 10 to the minus 11 at even longer averaging time. It's about 10 to the 4th second. So you can keep good stability over even longer distance, even longer time. This one is actually a pretty interesting measurement. So as I mentioned before, molecular rotation tends to be very stable against the magnetic disturbance. And indeed, we saw that. So in here, you can see that even if we change the environmental magnetic field by 75 Gauss, which is pretty strong, the change of the instantaneous frequency is still very small. It's below 1 ppb. So this is actually roughly 100 times better than the chip scale atomic clock, which has a dedicated magnetic shield in its package. So the last missing puzzle of this clock is actually the gas cell, because you can see that it's still pretty bulky. And this, right now we use a CNC metal machined gas cell, which is obviously not low cost. And the next step is to basically carve out these single mode waveguide out of a wafer, out of a silicon wafer. And we recently demonstrate that it's possible. Of course, there's still a lot of work to do to hermetically seal the gas inside through wafer bonding. But I definitely believe this is possible as well. And then we have an all silicon chip scale atomic clock, which has a much lower cost. And also one future direction that we are really excited about is to use even higher frequency transition lines at about, for example, 500 gigahertz. There you can see that the volume of the OCS gas is even smaller. And also the size of the waveguide is so small that you can directly carve it out from a silicon substrate of the chip itself. Okay, so now we can have in substrate gas cell from a CMOS chip. And then what you can imagine is it is truly chip scale. Now the size would be extremely small, which is a really interesting direction to go. All right, so I would just use maybe the last 5 minutes or so to quickly go over the third prototype that we have, which is a room temperature CMOS quantum magnetometer. This is a collaboration between my group and also Professor Dirk England's group at MIT. So essentially in here, the quantum system that we use is called the nitrogen vacancy centers in diamond. I believe ELP is very familiar with this material. So essentially what you have in here is a diamond carbon lattice, and then out of two adjacent carbon atoms, you replace them with one nitrogen atom and also one vacancy. And this turns out to have very good two-level system quantum transition in the room temperature, and more importantly, it's solid state, which means it's much easier to do the integration with the chip. And people use this for high sensitivity and also high spatial resolution magnetic sensing. I found this to be really amazing. Researchers can even do magnetic imaging for bacteria. So that sort of tells you the spatial resolutions and also the sensitivity of this technology. And the basic idea is right now the common, small, low-cost magnetic sensors are not that sensitive, okay? Versus if you use atomic vapors, squid, or other quantum sensors, they tend to have very good sensitivity, but the problem is the size is too big, the cost is too much, like this. So the idea is whether we can use CMOS to replace some of these hardwares, and then we can use CMOS to directly interact with the NV centers in diamond to achieve this high sensitivity magnetic detection. So here are some basics about NV centers in diamond. Essentially what's happening is there's two-level systems in the ground state, m equals to 0 and also m equals to plus minus 1. They are associated with a different spin direction, and they are separated by about 2.87 gigahertz. So really to detect whether I'm in the 0 state or plus minus 1 state, what people often do is to shine a green light onto this material so that the electrons are in the excitation state. And then when they relax back, they emit red photons. And if they are originally at the 0 state, they emit a much stronger red fluorescence light. But if they were in plus minus 1 state, they went through an intermediate non-radiative state and then get back. And then the associated red fluorescence light is much weaker. So now if you just imagine that I get the green light, and also I use a microwave field at around 2.87 gigahertz, and I sweep the frequency of this field. And also at the same time, if I monitor the red fluorescence, then what's happening is when the frequency is not hitting this transition frequency at 2.87 gigahertz, I'm in the zero state, and then the fluorescence light is stronger. But then when I hit the resonance, the red fluorescence is weaker. And then if I go past that resonance, the fluorescence is stronger again. So with the observation of this spectrum, then I can know whether this NV center is in zero state or plus minus one state. And people often call this optically detected magnetic resonance, or ODMR. Now, if I have a magnetic field, on this material, what's happening is now I have a Zeeman splitting, and then these plus one and minus one states are no longer degenerated. We have splitting, and the amount of split is linearly proportional to the magnetic field projection on this NV axis. All right. So now if I do the same ODMR procedure, I see two dips, and the distance between these two dips can be directly translated to the projection of a magnetic field vector on this NV axis. And what's nice about NV is we have four possible orientations. That means actually when I do this ODMR, overall I can measure four pairs of splits. And the amount of splits essentially tells me the projection of this field onto different directions. That means I can reconstruct not only just the amplitude, but also the direction of this magnetic field. So we have a vector field capability in here. And previously, people use large-scale instruments to do this experiment. And we believe we can use CMOS chip to replace those, simply because, number one, previously, people have to pump a lot of microwave power to really excite these NV states from 0 to plus minus 1. We found that it's actually not necessary, simply because of this very easy Ampere's law. If we can place the material to be super close to our microwave launcher so that the distance is much smaller, then without using much current inside this microwave launcher, we can have enough microwave field in the material. The other problem is we have to take out the green light in the system, because this remaining green light, when it goes through the diamond, can cause shot noise. But we don't really have color filters inside a CMOS electronic chip. And what we're doing here is to basically use metal gratings out of the back end of the line of CMOS technologies, and we can excite plasmonic wave in the vertical direction of these gratings. And the plasmonic loss tends to be wavelength dependent. So for green light, we have a stronger loss, a higher loss, and for red light, we have a weaker loss. That way, we allow the red fluorescence to go through. So this is the prototype. So essentially what you can see is we use loop inductors and a pretty small power to really excite the NV states. And the green light is external, but then we can use a built-in light filters and also photodetectors to detect the red fluorescence. And then we can see these Zeeman splittings and turn that into a magnetic sensor. The sensitivity is not great though. It's about 30 microtesla per root hertz. But later on, we improved the system by having a much larger diamond size. And also we use what we call a wired current array to really generate a very uniform microwave field on the surface of the chip to really excite a large number of NVs in coherent way. That way we can have much higher signal to noise ratio. We also use what we call multi-layer gratings to have better optical filtering performance. Essentially what's happening here is the first layer of grating generates diffraction patterns. And as we know, diffraction patterns has peak intensity somewhere and very low intensity somewhere else. And those positions are actually wavelength dependent. So if you can strategically place your second layer gratings and third layer gratings at the places where the intensity is peak for green light, but small intensity for red light, then you can select the red light further to go through these filters, and you can have much better optical filtering performance. So with that, we improved the sensitivity by about 100 times. And here's a demo. So the sensor is actually behind the curtain because we use laser here. And what you can see is as the student is moving the permanent magnet, then the sensor can generate in real time the vector field of this microwave of this magnetic field. And we believe with larger sensing area and even higher density of NVs, we can further improve the sensitivity to below nanotesla or even bigger improvement if we can have a spin control of the material. Normally, spin control requires a very uniform field inside the material. And as I mentioned, now with the CMOS chip, we enable that. Recently in the lab, we actually measured or we observed the Rabi oscillation of NV ensemble when this ensemble is driven by a microwave field generated by the chip. So this is a strong indication that the homogeneity of the field is good enough for us to do this spin control. All right, so with that, I would stop here. In conclusion, we are basically exploring a field that spans across circuit design and physics and electromagnetics, which can allow us to use low-cost integrated systems to do molecular gas sensing and high stability timekeeping magnetometries. And of course, people also do a lot of computing. So I believe this is only the beginning of the field. I think a lot more researchers should jump into this field. It's very interesting and very educational. And hopefully this can really thrive in the future. So with that, I would like to acknowledge my students, collaborators, and sponsors. I think I'm a little bit over time, so I can stop here and answer some questions.
Thank you so much for an excellent talk. This was really, really exciting.
Thank
we
you.
already have time for a few questions. I see Ali's hands up. Ali, why don't you ask a question?
All right. Thanks, Ronan. That was a really interesting talk. I had
you.
a question about your gas sensor. Could you show the spectrum that you had from that gas sensor? My main concern is with spurious frequencies. Since you have so many mixers, I wonder how you deal with all the spurious tones.
So you're talking about these spurs, right?
Exactly, yeah.
Yeah. So, I mean, we didn't really have any special treatment for those, but because we are using heterodyne down conversion, so what you can imagine is if this is the input spectrum of one channel, then that channel would literally have a LO signal that is roughly at this place. And then after the down conversion, although we have these spectral lines, but the down converted IF frequencies are much higher, then we can, just filter them out.
But isn't it possible that one of these spurs will fall right on top of the frequency that you're interested in?
We actually did the calculation, and we don't think that is the case. It could be possible. It could be possible that one curve in here is LO, and another curve that is has a slightly offsetting here is the input frequency, and they can, after the mixing of those, they can also generate IF. But the problem is, this down conversion process is a very strong function or highly dependent on the LO power, right? So if my LO power is 20 dB lower than the desired LO power, the conversion loss is just huge. And then you don't really have much impact out of these two, unintended mixing.
Yeah. Don't you get something similar to like, reciprocal mixing, where you basically you think you're sensing at one frequency, but there's a gas at another frequency that falls on top of one of these tones and then shows up. And so you would think that you're seeing the gas at frequency F1, but it's really at F2 due to reciprocal.
I think so. Just For example, if the conversion loss out of this desired mixing is, let's say, 10 dB, and the conversion loss of this undesired mixing is, let's say, 30 dB or 40 dB, I would imagine it's much higher than that. Then unless you have a molecule at that, different frequency, and the concentration or the intensity of that molecule is 100 times higher, otherwise you don't really have this interference. So I think in principle it can happen, but you need to have a very good sort of coincidence to make it happen.
So in other words, that you're limited in the dynamic range of sensing. If you have a strong concentration of A and a weak concentration of B, it can get swamped out due to reciprocal mixing.
Ideally, yes, but they also need to have just the right frequency.
Sure,
for example, right? So that transition needs to be precisely 40 gigahertz higher than this transition, which is still not that likely, but yeah, sometimes we cannot rule out that possibility.
The other question I had was on your plasmonic filter. Does that have angle dependency?
Does that have what?
Angle dependency? Does it still work if the green light is coming in at a different angle?
Oh, that's a good question. We actually, initially I thought we had, but so you're talking about this plasmonic filter, right?
Exactly, yeah.
Yeah, so initially I thought we have, but with some simulations, I think it's less likely, because the excitation of a plasmonic wave itself is not that sensitive to incident angle. And once you turn the wave into plasmonic wave, then it becomes less dependent on the incident angle. But indeed, in our experiment, we just try to shine our light in a certain angle. But the red fluorescence light is sort of, I believe it's sort of isotropic. We still see a good suppression or the good optical filtering performance. So it is my belief that this plasmonic loss dependent filter is less dependent on the incident angle.
Yeah, so it's a very cool demo you have too. I love that video. Thank you.
Thank you. Thank you.
All right, we have time for Clark's question.
Oh yeah, so I guess I can jump off of what some of Ali was asking about the gas sensor, but I won't. I guess I would ask one thing. Have you tried using this with a large number of analytes, and do you see that you get false alarm rates? You may not have done that, I suppose.
We only tried two molecule gas mixtures, mainly for the limitation of our setup. Yeah, so I guess that's the answer. I think at the physical level that shouldn't happen, because the research, like chemistry researchers, they have published tons of papers showing that you can really distinguish different transition lines out of a very complex mixture. But in our setup, we only tried two, as you can see in here.
Okay, that was just jumping off of what Ali was. My real question is more about the molecular clock, actually, in that 4 times 10 to the minus 11 in 1,000 seconds. That's awesome, actually. That's great performance. But when CSAC was at that level, they still could do better than that. And one of the things they found was that it was aging with a VCSEL, for example.
Yeah.
There was one thing they had to solve to do better than that. And so, would you think that you have a similar issue? What's preventing you from doing better? Is there aging of your terahertz circuits?
It's as I mentioned, only until recently can we start to measure to 10 to the 4th second, which is about like a half day. If you need multiple samples at that time scale, you can measure up to like 1 day or 2. So it's really about the quality of the gas cell. We find it very hard to have nice hermetic sealing of such low pressure. So in here, the pressure is only about a few millitorr. So it's pretty low pressure, and we need to keep it for a very long time, and we still have difficulty in that. We have outgassing issues, we have leakage issues. So beyond that, 10 to the 4th, we see that the Allen deviation goes back up, but we are not really sure. Actually, we don't believe it's due to the drift of the molecule itself, because we see that, you know, the pressure really goes down, and then the pressure really goes up, and then the purity really gets back. So that has been a very big issue that bothering us all time. But things are getting better, but, you know, with a very slow pace.
Sounds like you're about to solve it, because you said you were going to try to go to a silicon solution, which is going to be just like
Right.
the chip-scale atomic clock solutions, and those are very stable, actually. So if you could do that, yeah, it'd be very interesting.
I feel that with the surface quality of this clean room stuff, it's much better than this CNC machine, the waveguides. So hopefully we can solve that problem. But here we still sort of cheated, in the sense that we rely on a bigger space outside of the single mode waveguide, so that we can have less outgassing. But now if we really seal the gas inside that very little waveguide channel, the outgassing would be just worse. So there could be still quite some thorny problems to solve.
All right. Okay, super stuff, Ronan. I'll let Dorian
Thank you,
ask his
Clark.
question.
Well,
Thank
actually,
you.
you just answered it. I was going to ask about, if you make this thing smaller, does the problem get worse? My other question
so.
was, how much cheaper do you think one of these, that the molecular clock will be versus the atomic clock, specifically with the DARPA was just wasting a lot of money previously?
Well, I think just in terms of because I talked to the vendors of chip scale atomic clock. I think they particularly hate the VXL in there. They basically said that VXL has to be very stable, and it has a very specific wavelength to generate. So all those are really problematic. I think at least we don't have those fundamental issues in here. It's nothing more than just a CMOS chip plus a waveguide, which hopefully eventually is coming out of a wafer too. And the OCS gas itself is chemically pretty stable, and you also need to like evaporate it or something. It has the gas phase above like -50 Celsius. Yeah, so although it's too early to judge, but I would hope that eventually the overall cost would be kind of similar to just a CMOS chip plus some additional packaging cost.
I wonder whether you could actually find some sort of material that would sublimate to provide your gas at some constant, that would sublimate at a certain pressure, and so you just constantly have a source of gas of your molecule that you're measuring.
I don't know.
Then you don't have to worry about it. The leakage becomes less of an issue, and because it'll be a function of the pressure, it would stay relatively constant.
But we still need to have a certain range of pressure. It cannot be too high. So if the pressure is too high, we start to have this intermolecular collisions.
Right. No. You need pretty low pressure. I was just thinking that it was just at a source. I was thinking, but really impressive talk.
Thank you.
Okay, I'll allow myself to ask a last question. So I think this question is for both the waveguide you're showing here and also the dielectric one in silicon.
Okay.
Is there any reason you're using waveguides and structures that have many wavelengths inside? Like, could you push this to lambda/2 resonators that are low Q? Yeah, what's the reason for making?
Yeah,
waveguides?
that's a good question. So I think eventually the signal to noise ratio, which determines the short-term Allen deviation, is determined by, of course, your receiver noise, but also the amount of molecules which eventually generate that amount of absorption you have. So if you have a high Q resonator and then much more compact size and much less molecule in there, you can have more efficient usage of those molecules, but the total amount of absorption you can get is still small, simply because the high Q resonator itself would amplify the intensity in there. But if the intensity is too large, you saturate the molecules. Okay, so there's a certain amount of power that the molecules can swallow in the end. So it really doesn't matter if you have larger gas size or a smaller gas cell size, once they are smaller, then the total amount of power you can absorb is smaller, and then you don't really have a good SNR.
But I guess the single pass cross section is not unity. So if you have a molecule in a waveguide, it's not like it's giving all the signal it could give.
It's not very good efficiency, but it's okay, because if you think about really the wave distribution inside a single mode waveguide, right? It's pretty much the majority of the cross-sectional area is still interacting with the molecules, right? So you don't really just interact with the molecules on the peripheral, but other than that, it's still a good interaction. So we actually pump the power to the level that we start to see power saturation or power broadening of molecules. So that made us believe that that's the best you can have. But frankly speaking, we never tried resonator-based gas cells, so it could be something worth seeing.
All right, thanks so much. Yeah, this was a really exciting talk. Thank you for sharing your results with us, and thanks to everyone for joining. That's it. I guess we'll end here.
All right, very good talk. Very impressive.
Thank you.
Bye, everyone.
Bye-bye.
Thanks, Ronan.